Alright, another USACO silver problem. What's happening here? We have 100,000 farms forming a tree. And each farm is labeled with either G or H. We have M friends. Okay. And take us between two nodes or two farms. I see. And they want to visit nodes labeled G or H. So basically, we have this tree, we have a bunch of paths in the tree, and we want to find out, paths and H or G, and we want to find out if the path contains H or G. Seems like a very hard problem for solver. Okay, so you could probably do this with LCA. Okay, so what is going to be the idea here? So obviously the sort of brute force solution would be to walk the path from A to B and just see if you hit the target letter. But this is too slow because there's, the paths are of length 100,000 and there's 100,000 queries. So 10 to the 10 is too much. So we should try and do the queries in something like log n time. And so a way we can do that is this technique called LCA, which I will first try to explain and then code up. Yeah, I'm pretty sure this is going to work. And there's partial credit for basically the brute force, right? This would only be 10 to the 6, the NM solution. Okay, well, let's give it a try. Okay, so what do we have? We have N and M. I'm going to call N2 for queries. And then we have a list of edges. And probably 1 indexed. So we're going to 0 index. And the edges are bidirectional. And so E of A is just going to be the edges coming out of A. And then we have the queries. So this is supposed to tell us whether along this path there was a G and an H. Let's see. Gross, but whatever. Okay, so now we just need to write the query function. Okay, so as usual with trees, it's going to be helpful to root it. X, I'll fill in, like we're not taking E right now, we need to fill that in. If Y is not the parent, then y is a child. Root y x. Okay. Actually, I think we are going to want to know the parents. So we'll say that p of y equals x. And we'll just make e global to save a little bit of typing. Okay. So at this point we can root, and it doesn't matter what we make the root, so we'll just pick 0. And the root has no parent. Okay. So now that we have a rooted tree, we can think of our paths as follows. Right, so here we have the root, and there's some subtrees. So anyway, suppose we want to look at a path from A to B. The way that that path is going to look is that it's going to go up. Right. Right. Basically, it's going to go up to some point, and then it's going to go down to B. And that's always the case, right? Even if, maybe it goes only to PA, and then, B is a sibling of A. It could go down here. Maybe it needs to go up 2, but you can always, the path from A to B is always going to look like this. And so this sort of hinge point, when it goes from up to down, is called the LCA, or least common ancestor of A and B. So why is it called that? Well, it's the first ancestor of A and B that is an ancestor of both of them. Right, both A and B are descendants of this common ancestor. And it's least because it's the one that's sort of furthest down in the tree. Right, I mean, all of the parents of that guy are also common ancestors of A and B. But this guy's special because he's the sort of furthest down one. So what we're going to do, and the sort of general method of LCAs, maybe parent pointers and LCAs, is to say, okay, well, can we, it might take linear time to go up and down because, these up parts could be very long. Right, if the tree is very unbalanced, right, the tree can be very high depth. So we want to speed up the going up part. And we're going to do that by taking steps of powers of 2. So instead of just taking, going up 1 and up 1 and up 1 forever, we're going to go up, 32, and then 16, and then, whatever. We'll be able to get to this common ancestor in in log time instead of in linear time this way. So how do we take these big steps? Well, it depends sort of on the details of the exact problem, but you need to summarize, the step that you're taking. So in this case, what we care about is whether or not we saw G's or H's along the path. And so we're just going to write down for all the steps, so sort of the step from A to 8 above A, whether we encountered a G or an H, or both, along that path. So 2 bits per step. So to be a little bit more explicit, we are going to compute this vector of, I guess, this is a parent. This is going to be the key data structure. So the parent pointer of xk is the 2 to the kth ancestor of x, whether there is a g, whether there is an h along that path. So we're going to compute this for all all nodes x and all log depths k. There's n of these and log n of these, so this is an n log n sort of, bits of memory. Okay, yes, I said that the ancestor comes first. Fine. These should really be bools. But because of this weird thing with vector bool, I'm always scared of bools, and so we'll use ints. It's, it would save a little bit of memory to use bools, but it's not a big deal. We're not within a factor of 4 of running out of memory. So anyway, the basic plan is that we're going to fill in this data structure, and then to actually traverse a path from A to B, we're going to walk up the data structure quickly to the LCA, and then we'll figure out like which G's and H's we saw along those paths, and we can return that. So by the way, how do you actually get to the LCA? Well, we're also going to compute a depth for each node. Which we will fill in here. So I guess we want to know the depth. D of x is d, and this is just d plus 1. So this is like how far away you are from the root. So d of root is 0, d of child of the root is 1. And the point of the LCA is that the LCA is... Right, so how would you find the LCA of A and B? Well, you just walk up whichever one of them is further down in the tree until they're equal, and then you keep walking them up in lockstep until you're at the same node. Right, you know that the LCA, has some certain depth, right, some unknown depth, but the LCA, it's the same for A and B, obviously, because it's only one node. So if you keep walking A and B, right, so first walk, the deeper one of A and B up until it's the same depth as the other one, and then you have ancestors of both of them at the same depth, and keep walking them up, and eventually they're going to become the same node. And so that, yeah, that's the plan, and you'll see in more detail when I actually implement it. Okay. Right, so the depth of the root is 0. That's what this call is all about. Okay, so maybe I'll write, well, we'll just do it here. Okay, so we need to initialize d. We'll just set -1. Okay, so now that we've sort of done the roots, computed the children, actually we don't even care about the children, and the parents, which we do care about. Maybe I'll just delete children, so we are not going to use it. Now I'll compute the parent pointers. Right, so we want how do we compute log in C++? It's annoying that these things return doubles. Really shouldn't. Equals log 2 of n plus 1. Something like this. This maybe is a little bit too high, but that's fine for a little bit too high. Actually, let's say 30. Right, certainly n is less than 2 to the 30. Maybe it's probably even less than 2 to the 20. Okay, so parent pointers is going to be a vector of vectors, and each of those is going to be no, it's not a it's a vector of this thing, which which is this thing. So what happens? Okay, so a step of size 0 just goes to the parent. And what does it have a G? I see. This, I see. Okay, I missed a line of the input, which is the sort of labels on all of the nodes. I'll use C for color. And G will be true. Okay, it's confusing to use bools, so just do it this way. Or C of PI, H, or C of PI is H. Yeah, this will be fine. So, okay, so we're saying that to take a step, when you take a step of size 0, you go to the parent, and you've seen a G if either your current node is G, or the parent is G, or your current node, and you've seen an H if your current node is H, or the parent is H. Okay, so fine. This can be vector char. And we're going to use, okay, so how do we actually fill in PP? So we use the fact that a step of size, 2 to the n is 2 steps of size 2 to the n minus 1, right? That's the point of the powers of 2, is that the bigger step is composed of 2 of the, previous step. So PPIK is so first take the step of size k minus 1, which brings you to some node and possibly seeing some h or some g. And then to take the step of size k, right, and then you can take a step of size k minus 1 from that node that you first saw. So you end up at P2, and we saw G if we have G1 or G2, and we saw an H if we have H1 or H2. Okay, so now we filled in PP, and now we can do query from A to B. So first we're going to take steps until the we first saw G and saw H, which is ultimately what we're going to return. So consider all these steps So we're going to take steps until they have the same depth. So if A is deeper than B, then we want it So after this step, if we take a step from A, if we take a step from A of size k, then we will be at depth dA, not plus but minus 2 to the k. So if that's still bigger, but if we're still deeper than b, then we want to take that step. I guess greater than or equal to, because we want to be equal to b at the end. So if we actually take this step, then if we saw a G or an H along, this step, then we can mark that off. And we send A to, the destination. And then the same thing for B. So now we should have that dA equals dB. And now we're actually going to find the LCA. So the way we're going to do that is very similar, except that we're going to take the step if they're not equal. Maybe it's better to write it like this. So figure out, what the step would look like for both of them, and take the step. Right, if the new location would be less steep, let's maybe go through a way to write it. And we're going to take this step. We want to get to the biggest node where they're not the same. So we're trying to get them both to one step below the LCA right now. So go to the sort of highest step that they're not the same, and then we'll take one more step at the end to actually get to the LCA. So as long as they're not the same, you want to take the step. So in this case, we want to take the step for both of them. So this is HA and HB. A equals PA, B equals PB. Okay. So they should still be equal, since we only took equal steps of both of them. And now it should be the case that their parents are equal. There's a special case where A is actually the same as B, in which case, they will be equal the whole time. But this assert is still true in that case. So if they're still different, then take one more small step to both of the parents, so a step of size 0. Now they should be equal. And along the way, we traversed sort of all these edges. We kept track of whether we'd seen G or H, so now just return whether we saw G and H. And that's actually all of the steps. Maybe we forgot to import vector. Yes. Utility for pair. Maybe I gave pp the wrong type. Yeah, it should be not a vector of this state, but actually a vector of vectors. Yes, let's see assert, so that we run all our assert statements. I see. Yes, and we also have the colors. Not LL, but char. This is not a vector of LL, but a vector of this weird tuple. Maybe I should have given it a name. Let's see. Should write tuple. And again, I should write tuple. Ah, it compiles. Amazing. Okay, crashes. Let's figure out where. Okay, so somewhere in here. Somewhere in here. I see. Yes. What happens if we go sort of past the end? So if you try to go sort of past the end, and you can't take another step, right? So imagine you're the root. What does even your size 0 step look like? We shouldn't look at anything with the parent if we are going past the end. And if the step takes us past the end, then we should okay, well, I'll just be a little bit naughty and handle this case in a simpler way, which is I'll just say that the parent of the root is itself. And then I think that cleans up all these special cases. And just check. That all the parents are good. Okay, so this does now run, but it gives us the wrong answer on the third query. from 1 to 3. We'll just initialize to. All right, we know the path from A to B is going to have to hit A and B. So if either of those are G or H, it must be good. Why did this happen? I guess if you take no steps, we were always setting. We were never setting G and H. But I don't understand why the path from 1 to 3 only had H. Okay, there's some inelegance here. I think maybe we don't need this part. Basically, these segments that I'm sort of thinking about, right, represented by PPI, there's some question about whether they're inclusive or exclusive on the ends. So right now, I've tried to make it inclusive on both ends. Which is fine for this problem, but in different problems that would do some double counting. Yeah, so I still don't understand why this path from 0 to 2 doesn't have a G in it. Like this, I think this should have GB equals 1. Well, this should be P of BK instead of P of AK. And similarly down here. And similarly down here. Okay, well, I'm glad we caught that. Okay, good. 0.0110. Okay, well that was right. And we need to, okay, so I'm going to try and see if this, I'm going to submit this and see if it's right. To do that, we need to do the f3open thing. And this one is milk visits. Okay. All right, so let's see if this is right or not. It's not right. But it is mostly right. Okay. I think that 20 might not have been enough. Let's try 25. Right, because the first one is size of 1, 2 to the 0. Last one would be a step size of 2 to the 19. It's 524,288, which is less than a million. So that probably should have been fine though, because the step sizes of, 2 to the 19 plus 2 to the 18 and so on is 2 to the 20 minus 1, which is big enough. So that's a little sketchy, but I don't think it's an actual bug. So where's the actual bug? AAA, DDP, AAA, BBBB, GA or GB, HA or HB, A goes to PA, B goes to PB. DA should be equal to DB, PA should be equal to PB. Step size of 1, A, B, 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 B. Again, I guess we'll do GA or GB, HA or HB. A goes to PA, B goes to PB. Perhaps special case this. Then we can have the assert A is not equal to B. And then we can do this part unconditionally. 2 from pi, step size of k minus 1. We're filling this in the right order, right? We fill in all of the k's before any of the k plus 1s, since they all rely on k minus 1 steps. Right, the queries are A, B, and the character. Okay, I haven't really spotted a bug yet. Made a bunch of sort of, say, cleanup changes. Shouldn't actually have affected anything. Ah, yeah, I've got to add this assertion which failed, so that's nice. Okay, right. So there's this case where the LCA is one of them, and then this step to equalize the depths will actually bring them up to equality. So we can cut off here. Okay. Just try this. Still fails this test case. Still the same set of bugs, which I guess makes sense since I didn't actually spot any bugs. Definitely n-1 edges. Is it a wrong answer or a crash? I'm not sure. It's a wrong answer. Let me just intentionally crash and see what it does. Is this going to look any different than the wrong answers? Yeah. Okay. So that means that all my assertions are passing. I'm going to correct this sort of double counting issue that I mentioned before, which is that that it doesn't count the base being a GOH, but that, I mean, we're counting it here, right? That shouldn't matter. So where's the thing that should matter? Okay, that looks correct. another slightly sketchy thing I did was setting this, handling the parent of the root. Maybe we can try and handle it more properly. So you should never take steps to -1. Did we not initialize the colors? It's the stuff happening after. Why is it not initializing the colors here? Oh, we have another variable called C. How did that compile? Okay, that was probably the issue. That would have caused us to fail on any query where A equals B. Yeah. Nasty bug. Alright, that's this problem. Seems very hard for a slow problem.